Good morning, participants. Uh, Welcome to the fifth day of 1 week faculty development program sponsored by AICTE ISTE on theory and practical essence of bridge engineering. So today we'll start with the first session of day 5. So I would like to introduce the speaker for this particular session, Dr. N.S. Kumar. He is professor and head of Gaussiya College of Engineering, Ramnagara. He graduated in the year 1985 from University of Mysore, ME in Structural Engineering in the year 1988 from Bangalore University, and earned his PhD from Bangalore University during the year 2006. Then he has joined as a faculty in Civil Engineering Department of Gaussiya. Before that, he has joined in a Torch Steel Research Foundation, Torch Steel Research Foundation, Bangalore, during 1988 to 89 as an engineer, and later he has joined in Gaussiya College of Engineering in the year 1989. Presently, he is working as professor and head of the Civil Engineering Department and former director of R&D for a period of more than 10 years. He is involved in research in the field of related to behavior of composite steel columns and nanomaterials since a decade. As on date, he has completed 32 years of teaching and research experience. He has guided one MSc Engineering by Research, 3 PhD from VTU Belgavi. Presently, he is guiding 5 research scholars under VTU Belgavi. To his credit, he has authored 7 books on structural engineering, syllabus preparing to Bangalore University and VTU. He has also presented more than 4 research papers at international conferences held at USA, Canada, China, and Australia. To his credit, he has more than 200 publications in national and international journals. He has completed one VTU and R&D project work worth 15 lakh rupees, working presently on nanotechnology, uh, nanotechnology under the project sponsored by VGSD worth of rupees 40 lakh. He is also on the board of reviewers for more than 10 international journals, including ASCE Journal of Materials USA. He is also a member of NBA New Delhi, Local Inspection Committee VTU Belgavi, BOE for Bangalore University and VTU Belgavi. He is also a nominee for Dr. Ambedkar Institute of Technology, Bangalore. And he has also earned a series of awards. To name few of them: Dr. Mumtaz Ahmad Khan Award for Distinguished Exemplary Service in Community in the year 2011, Educational Icon Award by International Chamber of Service Industry, New Delhi in the year 2020, Award of Excellence in Research 2021, awarded by Novel Research Academy, Puducherry, India in the year 2021, and recently he has been awarded with B.K. Ramaya Memorial Award 2022, conferred for excellent career achievement in the year 2022. So on the behalf of technical institutes such as ISTE, Association of Civil Engineers, Institutions Innovation Council, Atal ranking of institution achievements. So with this brief introduction, I would like to present before you Sri Dr. N.S. Kumar. Welcome, sir.
Thank you.
And it's a pleasure for us to be a part of this particular program. Welcome you, sir.
Thank you. Now I will be starting, sir.
Yeah. So I request you to take over the session, sir.
Thank you very much. Good morning to you all the participants. At the outset, I thank the all organizers for giving me an opportunity to deliver this talk in the FDP 5-day FDP, which is AICT IST sponsored refresher program. It's a very good subject. It's a theory and practical essence of bridge engineering. Already this is the fifth day, so I am going to present whatever I have. I have done this work myself for my research. Dynamic response of slant-led skew bridges. This is the topic. As all of you know, among the civil engineering systems, road system is an enormous national asset. All of us know it. Nowadays, they are investing a lot on building the super this one and flyovers, bridges. So it also helps us even in commerce, communication, like economic growth, as you know, even in social development. To meet the need of the modern society, we know that advanced transportation system, more and more bridges have been built throughout the world. So the question is here, usual bridges we used to design and all, and many are talking only about static analysis. Now what research we have done is with billion ton miles of commercial traffic nowadays, we have to give importance to the dynamic response. Moving dynamic vehicles will create a lot of dynamic stresses on the pavement, and we have to take care of that. Even in the bridge code books they are implementing this, especially in abroad. A lot of this one they have done. Even in India now they are taking a lot of care. What is this? There are two types of responses. One is static response, another is dynamic response. This is the response due to moving load. A load which is a function of time is called dynamic load, and the response due to that is known as the dynamic response. The very interesting fact is dynamic response is very high than the static response. This is a very important point. And also VBI studies are very important nowadays. That is called vehicle bridge interaction. It's a commonly encountered in all the transportation facilities such as highway bridges, railway bridges, aircraft, bridges in airports, so on. Now we are highly concentrated on this only. And in general, many of the students, maybe audience or many of the faculties are here. All of you know that bridges are subjected to time dependent forces. For example, we used to take usual dead load, live load, wind load for all the loads to be taken in the design. And impact also due to moving load is to be considered, including earthquake. Now the forces to be considered usually for superstructure is, we know, longitudinal forces due to vehicles tractive effect, and also frictional resistance we should not neglect it due to expansion bearings, and also curvature we get centrifugal forces. So these are the very important things we have to take into account while designing the due to dynamic. Now when you come to the particular, slant leg bridge is one among the highway and railway bridges. The point is superstructure and substructures are treated as one unit in this case. It consists of infinite degrees of freedom. Degrees of freedom in our dynamic analysis, it is infinite because it is not discretized. Overall, if you say is a infinite degree, it will eliminate the piers, only left abutment and right abutment, and also it will help in it is away from the lower roadway. These are all the important things. Example how it looks, slant glide skew bridges. Example is in Switzerland existing, which is of 70 meters. Span is 18 to left, in the middle 34, 18 to the right. So we say it as 18, 34, 18. If we add, it is coming to 70 meters. Distance between the foundations existing 55 meters, I mean 5.5 meter, and width is 6.5 meter. Construction height of the superstructure in the center of the bridge, these are the data available. Height above the ground is approximately. See, the main point is to the left and to the right. This is a clear way so that vehicular traffic is unaffected because there is no piers at all. Only left one slant, right one connected to the right bund. So this is what is known as slant-like skew bridge. Some of the examples I am showing you with all the details near, see this one Germany, and near this Switzerland and this border, all these are existing structures. This is the importance. For example, Bedford County, we call it as in Pennsylvania. This is around 125 feet. Total length is 227 feet. Width of the deck is 38.1 feet. See this figure. This is existing. So these are all some examples I am telling you. Even in Missouri, length of the largest span is 118 feet. Total length is 315. Deck width, you see, 28 feet. This is the existing. So we thought of doing some analysis on this. One car, even this example of New Hampshire, dimensional length is 160, but the question is 295 feet it is, width of the deck is 65, angle is 10 degrees. So as you go on changing the skew angle, what happens and what will be the maximum angle? This is our main point of research. So this is why I wanted to talk on this and how they have done in abroad. These are all the existing things. Now you come to next slide. You see here, 295 feet plus 650 feet deck width. Now if you see this, one minute. So I am giving you the examples of all this, New Hampshire and all that. Now you go to the next slide. Next slide. Here, this is in Pennsylvania County, Lake County, we call it as 315 feet. These are all examples to show you that I'm not talking simply. These are all existing in abroad. So based on this, I am going to present now. Now the question is, be dynamic stresses are greater than those at static loads. As I have told you already, dynamic response of a bridge resulting from the passage of moving vehicles. It is a very important study. And now, how do you classify this is the first point. We are having either we can take it as a continuous mass or as a discrete mass. This is what we teach even for students in dynamic classes. It means either it's a lumped mass approach or it may be continuum approach. And one more is here, that is called orthotropic plate theory we are using. It is 2D and there is a continuous mass distribution here. So either we can use this type of theory or we go for, nowadays a lot of softwares have come, that is finite element method, we use discrete theory. So overall we have continuous mass distribution, discrete theory, orthotropic plate theory. It is 2D. So now you see, coming on to lumped mass approach, we have 1D, 2D and 3D. This is how we study the dynamic response in case of any structure. Now in particular to the bridges. So this depends upon, for example, this depends upon this depends on vehicle parameters, bridge parameters. This depends on vehicle parameters and bridge parameters, and lot of vehicle parameters have to be considered. For example, see, there are so many parameters are there in vehicle, and following are the important things we are considering. One is speed of the vehicle, number of axles, mass of the vehicle, damping, type of vehicle suspension, it may be sprung or unsprung, axle length, spacing of the axle. So these are the things we are considering. Now, what is the, already we have done a lot of research that is called your literature review. If you go through this, it started in the year 74 itself by Gobara and Toss. That paper is available. They analyzed the foothill boulevard under crossing South Bridge. So this is one of the starting. Next, so many people contributed. Example, I am giving you in 1991, 94, 95, and in 2001, also from, he was my guide, Munirudrappayan, my PhD guide, and his student. They also studied rigid frame bridge. So we have rigid frame bridges and also some skewed RC box girder bridges and slant like rigid frame bridge also by Wang. These are some of the literature review I did. Then what is the work? Some of the parameters to be considered are, as I have told you already, mainly in this work, axle spacing we have to consider, vehicle speed, damping of the vehicle, all this regarding vehicle. But regarding bridge, we have to consider the span, stiffness, mass, damping, skew, pavement roughness is also a very important factor. Roughness coefficients, surface roughness, all this should be considered, and spacing of longitudinal and cross beams. So these are the things to be considered. But actual work, what is involved in this report is free vibration studies, forced vibration studies, and how to assess surface roughness related to dynamic response, vehicle bridge interaction studies, VBIE we call it as, modern structural control systems. Nowadays they are using tuned mass dampers. This is to be adopted to achieve the desirable response for an external load. So these are the present study. What is done is, either we can't give a choice. We are doing both free vibration also, forced vibration also, along with VBI, vehicle bridge interaction has to be considered. Now you come on to this whole topic is based on one factor that is called dynamic load factor or dynamic amplification factor, that is called DAF. Hope I am. Is it okay? Audible, participants? Hello, hello,
Yes,
sir.
sir. Yes, sir. Yes,
Okay.
sir.
Uh,
Audible, sir. Audible, sir.
Thank you. What is happening in this whole topic is load factor. We all know. In case of that, we used to call it as a DLF in this topic because it's a due to dynamic. DAF means it is a dynamic deflection to static deflection. The ratio of dynamic deflection due to movement of vehicles divided by static means due to self weight maybe. So dynamic deflection to static deflection is the very important study here. That is called DLF, and it's a function of natural period of the structure. Period. You know, it is one over f, 1 over frequency natural is called natural period. It's a reciprocal of the frequency. So this to the how much time it that impulse is there. Impulse may be any shape we take for analysis. It may be trapezoidal, rectangle, triangle. It's a small time for a small duration. A large force will be acting. So a force acting for which is very high in magnitude, but time duration is in seconds. That is called as impulse. So what is this natural period of the structure? First we should calculate, and if you divide it by the impulse of the duration in seconds, and this is also very important factor. So dynamic load factor is also called as DAF, dynamic amplification factor. Point is, what is the range? It is a ratio. It has no units. It's a number. It is between 1.5 or 1.2 to 2 maximum. So this factor has to be considered in the codes, which is actually not much considered, which is missing in Indian codes. Very, very important. Now they are giving the importance in highway and also in all the bridge codes. All the codes, it should be coded, and this should be a must for considering the DLFs. So this is what we started the analysis. And as I told you, free vibration and forced vibration studies has to be done. In this particular type, what is to be done? First, I have to model it. All of you know. It's a space frame. And degrees of freedom, we are going to divide into number of nodes. How many freedoms are there? There are delta x, delta y, delta z. It means what? Displacements will be there along x direction, y direction, and z direction. Along with the displacement, there will be rotations. That is called theta x, theta y, you know, and theta z. So 3 plus 3, 3 displacements in 3 rotations will give you 6 degrees of freedom per node. This it is an element stiffness matrix has to be created. And we all know what is the meaning of that. See, K we know, matrix we have to generate. For that, we have to go for geometric stiffness matrix. So K is equal to K1 linear, KL or K1 linear stiffness matrix. We have to add to the geometric stiffness matrix. So this element stiffness matrix should be developed first of all in its local axis. Then it will be transferred to global axis by multiplying with transformation matrix. This is the procedure in dynamic analysis. So transformation matrix is used for just like a load factor. We have to multiply the existing element stiffness matrix. So this is the procedure used using the mathematical formula and matrix analysis. Then we go for any software available. So now by combining the entire element stiffness matrix, we go for global stiffness matrix, which has to be obtained, which in turn will be used to find what? Static deflections at each node. That I will be showing you how many nodes we have considered, why we have considered, how to analyze. So the free vibration of the slant bridge is studied by which method? Jacobi, he has given the particular method in mathematical analysis, which will represent an eigenvalue problem, which we know in all our dynamic analysis. We know the meaning of standard eigenvalue problem, and the solution of which will give n number of natural frequencies, and where n is the degree of freedom and lambda represents the natural frequency. So based on this, each lambda, we get a vector. No, it can be evaluated representing the natural mode or principal mode of vibration. So a parametric study will be done here in order to study the effect of the skew angle and span of the bridge. So this is the whole story for free analysis. Okay. How to do this formulation of stiffness matrix? If we are strong in mathematics or we know the background of matrix analysis of structures and structural dynamics, we can formulate member stiffness matrix. This is what I have explained here in detail. You please see in this sketch, space bar element, example I and J nodes, one bar I am explaining. As I told you, there are 6 degrees of freedom to the left, 6 degrees of freedom to the right, 3 rotations, 3 displacements. Therefore, theta I, theta theta zi, theta xi, theta yi. Then I am giving you all the symbols I am showing you. It's a one element. Now you go to this is what I have done, and that I am explaining one by one. Each ui, vi mean these are the displacements. All are transverse displacement in x, y, and z directions. And for rotational displacements, theta x, theta y, and theta z. Then we know the standard element stiffness matrix. I told you it should be added linear plus geometric. So after getting this, I must go for final. For final, I must go the transformation matrix. What is that? I am explaining here. It's a diagonal matrix. Only diagonal elements are available. R. All are 0, 0, 0, and it is 4 by 4 size. Now you go to next one. These are all much of mathematics. Just to show you, I am explaining. All these are basics. Next one. See here. This is what. Finally, we get the stiffness matrix. Okay, that is the transpose or transpose Km into R. This is usual. We know how to do this. This is the formulation. Similarly, finally, how to get, it's the summation of from one element to any number of elements. I is equal to 1 to m. Each we have to take the sigma. So this is represents the element stiffness matrix. Now this is regarding what? Free vibration dynamic. Now you come to static. Static, we know F is equal to K delta or Ku. Same formula, but the question is F is a vector, K is a matrix form, and U is displacements. Displacement vector, load vector, and structural stiffness matrix. Already I have explained. It's a square. The above equation has to be solved for displacement vector, and what method is to be used is the point. Finally, it has been, we have, after going through the literature review and so many things, Cholesky method of decomposition is the best. And this is a one very easy procedure which many have learned in our mathematics in UG and PG classes. Cholesky method of decomposition will be used, and we are going to get the displacement vectors. So now this is what is finally the basic dynamic equilibrium equation using Newton's second law. All we know. What is that? Mx double dot plus Cx dot, same type. Here it is My double dot plus Cy dot, any symbols, same type. Mass matrix, damping matrix, Ky, stiffness matrix into deflection, which is equal, it's a forced vibration. So it is not zero, it's some force is there. That is a column matrix of the applied time dependent forces. This is the general dynamic basic equilibrium equation. As per your Newton's second law, we are doing this using D'Alembert's principle. Suppose if f of t is 0 on the RHS, then we know it becomes what? My double dot plus Ky. If it is no damping, undamped, no force, free. So all this we know. If you put f as 0, it becomes free. No damping means C matrix will be vanishing. And you get only My double dot plus Ky equal to 0. These are all standard dynamic procedure. And this is done by Fourier. And he is telling how to do this. Periodic motion can be represented by a series of sines and cosines in Fourier series. This is what the whole thing we have applied here. And hence you know all this mathematical background, Y double dot, how to find the acceleration. Then finally the form will be m minus lambda k of an equal to 0. The above equation represents generalized eigenvalue problem, which we have already I told you. And to get a non-trivial solution, we know determinant must vanish. No, determinant corresponding to this vanishes. So this is the procedure for all structural dynamic problems. The above determinant, we call it as frequency determinant. Solution of this will give you nowadays very easy because of the softwares are available. We need not do hand calculations. You get in seconds all values of natural frequencies. And also n is the degrees of freedom, and you get all natural modes or principal modes of vibrations we get. Then after getting this, how to convert the generalized eigenvalue problem to standard problem? That is the next step. All this I have explained, just I am repeating it. And finally, I told you I am using what is known as Cholesky's method. Okay. After explaining all this, suppose you come to numerical computations, how to find what? Idea is to find natural frequencies. Computer programs should be developed, which has been I have developed for my research work here. That's why what I did I am explaining. Okay, using the MATLAB in those days. And these programs were developed taking into account elements in slantless rigid frame as a beam element in space with 6 degrees of freedom. I explained different cross sections you sketch are all considered and skew angles are varied. What is the objective? To know the effect of increase in span on the frequencies. As span increases, what happens to frequencies and effect of skew on fundamental frequencies. These are the two parameters taken for study, and bridge is modeled as a space bar. Already I told you as 6 degrees of freedom, and this span for consideration 20, 32, 20. So it will be 72 meters. Slant legs are at 45 starting. Cross beams are spaced at 8. Longitudinal beams are at around 4 meter. Cross sections were considered are T section, I section, box section. So these three sections were taken into consideration for our study with 45 degrees slant. Then what happens? All these were I have modeled using SAP 2000. So what happened after modeling? We came to know we got some first five frequencies which are very very important for both 1D and 2D behavior, and different spans are also considered. I told you 12, 15, 12, 15, 18, 15, 17, 21, 17 like that. And we have taken three sections T, I and box. It is observed that as span increases, frequency decreases. That is the first point. Second is with respect to skew. As skew increases, it was observed that fundamental frequency tends to increase non-linearly. So we should be careful about skew angles. It is a non-linear increase. So for an increase of 50, frequency increase is 5 to 7%, which is verified with the work carried out at University of Rolla, Missouri on dynamic signatures of the test results. Those results again I verified, and we came to know from our experiment the skew is inducing flexibility in the structure. Correct. Then all the frequency tables and all the cross sections I am showing you in the next few slides. So final conclusions, what is that I told you? Frequency decreases as span increases. Skew increases, frequency increases linearly. After certain degree of skew, it becomes non-linear, and that is a very important. And for the range will be around 5 to 7%. These are the what we have observed in our research study. So this is the just result analysis. Frequencies F1, F2, F3, F4, first 5 frequencies. Spans have considered for our analysis. These are the frequencies. And slantless skew bridge of 1D, one dimensional, area of the T section, moment of inertia for this. Similarly for 2D, what are the changes? Similarly for this one, what free vibration for I section, free vibrations for T section. Again 5 frequencies. All these were calculated including box section with zero skew also. Means without skew, then we went for skew increase. So these are the very important studies have been done for all the types of sections, and we use this analytical model of the bridge because we have to analyze. No, so how many nodes? 17 nodes. 1, 2, 3, 4, 5, 6, 7. See here, the deck has been discretized, and the slant is not 5 to 16 is one stick. 11th node to 17th node is one stick. So 5 to 16 and 11 to 17 slowly between 0 means no skew. Next you go to 10 degree, 12 degree like that. Minimum and maximum we have to fix so that at what stage you will get non-linear skew variations. That was also checked. So this is what actually done for our analysis pre-vibration using SAP 2000. This is the model you are showing. See this, you are seeing the screenshots. What is done? It's not simply somebody's work. It is my work for my research. This is the thing. And also these are your variations. What CPS, okay, cycles per second frequency versus skew degree between 0 to 50 degree variations, fundamental frequency versus skew angle. Example, one span I am showing you like that. All the spans were analyzed, and these are the plots for all the different ones using SAP. This is the modes of vibrations you are seeing here. Period is 0.21 seconds for this span. Cross section is shown. Frequency 4 hertz, 4.6. No skew. Suppose skew goes on increasing, what happens to the period? Frequency, cross section is how much? All this it is more than 6 years of study. So all these models I am showing you with 0 degree. These are the for different spans. Figure free vibration mode shapes. Okay, and I felt that 4.21 CPS is okay for the particular span. This is the sketch. So now you see this is for different 16, 32, 16, and also for T section of same span, different span is same, cross section is varied for different skews and same skew. So all these sketches you can understand. So this is how I came to know which is a very important factor for free. Then we thought of doing forced. In case of forced, I told you what force I have to take. It's a time varying external load, as you know, it's a dynamic loading, and it's a very complex phenomena because I have to consider interaction between the bridge and the vehicle. That is the main point. And we know in our dynamics so many types of impulses. Usual moving triangular pulse is the best for such studies for highway engineering, for traffic. Therefore, we have taken moving triangular pulse. And this was, first of all, is it okay or not, was checked with a very important fundamental paper was from Philo. He is a very important person, father of structural dynamics, Philo. And his paper, known as Dynamic Influence Lines for Beams and Frames, in the year 96, it has been implemented using MATLAB. We have changed it to, first we wanted to verify the results, then the speed of the vehicle, usual 30 km per hour to 60 kmph, using impact factor, and its range on the slanted bridge is also considered. Philo, I was telling, he developed a general method for calculating response using constant force moving at constant velocity, using discrete model for mass distribution. Now the question is moving force, how to idealize using a triangular pulse. And he adopted Laplace transforms to get the closed form solution. You know there will be a open bound solution in closed form in mathematics, higher engineering, mathematics, and we have studied, and using those things we have plotted dynamic influence lines. So in this present work, what I am going to present you is same type forced vibration. My double dot plus Cy dot plus Ky is f of t. And this one is W into zeta t means what? One is column matrix of dynamic factors related to each normal mode multiplied by total weight. No, that is your matrix of amplitudes we call. Those two, if you multiply, you get d of t. This is how we did the forced vibration, and the same thing you are understanding here. You please see all our diagonal matrix plotting. Next we multiply by column matrix, then it will be square matrix of squares of natural frequencies. That is called eigenvalues. Eigenvalue means square of the natural frequency. If you take the square root, you get the natural frequency. So this is the background, and if you understand the background, it will be very easy to carry out the research. So these are the equations, and using dynamic factors, these equations, one who is interested can go through Laplace transforms, and you have to model all these things. And finally, static influence line of deflections are obtained using triangular force. And which method? There are so many methods. Best method was modal superposition method, and this is the equation which we have used in MATLAB programming. We have done this. So numerical analysis, same as what I did for free vibration. Now I am showing you forced vibration studies. How to do it using model. In those days also we have used SAP. Now there are so many better softwares you can verify for next research continuation by research scholars, those who are interested in this field. Okay, there are different spans were considered. Centered enter is 4 meter, and we developed the program in MATLAB 6.5 version with the help of Similinks. And also EWM is one of the methods, exponential window method. It's one of the method in using Similinks, and it was run for all the different cross-sectional properties. Speed were considered 30 kmph, 45, 60, 90, 120, different range, no vehicle speeds, and we have calculated the frequencies for and node positions. DLF, as I explained, it is found in the central position of the load by using the equations developed. So all these final results I am showing you for 30 how much, 45 how much, 60 how much, all the results I am showing you. Spans were considered was 64, 72, 80, because existing bridges also I showed you. It can be found that Skew has no effect on DAF. Okay, that is very important in case of forced vibrations. And these studies for different spans, and DIF variation is negligible from all the observations. So DIF range, how much we got it? Between 1.81 to 1.878. No units for that. Therefore, largest dynamic load factor where it occurred was center of the midspan. Midspan center. Dynamic load factor increases with vehicle speed. If vehicle speed is increased, then DLF were increasing. DLF increases with as span increases. Span of the bridge increases, DLF increases. Vehicle speed increases, DLF increased. And where you got maximum? Mid of the center of the mid span of the bridge. Irrespective of cross sections, for example, we took box, I, rectangle, irrespective of the shape of that, there is no appreciable change in DLF. DLF is independent of cross section shape. Skew has no effect on DLF. These are all the very important conclusions. And also, finally, forced vibration studies. These are the conclusions. I explained you for free vibration study. So after these two studies, we should not stop because the vehicle has to move on the bridge and lot of this one is there. Therefore, what we have done is two-dimensional slides of the roads were taken. Two-dimensional slides. Two-dimensional road surface. This is very important for road surface roughness. And see here, variation of the road surface profile along the longitudinal axis. This is a very, very important variation of the road surface profile along the longitudinal axis, how it looks. This was considered for the next study. That is called, what we did was road roughness surface analysis. So a lot of some of the papers searched were in 1974 by Dots, and he is telling the roughness coefficient, how to consider, and we call it as power density. Unit is meter cube per cycle. And also one of from China, 1995, Liu et al. Some of them have already studied PSD, that is called as power spectral density functions. And using this road roughness were calculated. Then present study, road roughness was zero mean stationary Gaussian. Random process were considered in the mathematics, and I have solved all these equations. Artificial road profile generator is a software tool which we have developed, and already from MATLAB 6.1 version, PCWIN we call, to evaluate the road surface profile with and without camber was also considered. This is what the approach I have explained. Define the system and define the components. Formulate the mathematical model, list the required assumptions, write the differential equations, describe the model, because I am talking of vehicle bridge interaction model, which should be, it's a coupled system. Solve the equation for desired output, examine the solutions and assumptions. If necessary, you have to reanalyze and redesign. These are the steps followed for this. Please see here, vehicle model considered as per ASTO, as per your specifications, HS2044, all these as spring mass systems, front tire, rear tire, middle tire, combined weight on the first two axles, all these were considered as per standard only. Then this is the model which is moving on the created model in the software, 3D moving vehicle, spring mass systems, you are showing with damping. Okay, next comes your actual model. I explained differential equation, that is same as almost mx double dot, same type, but here with respect to mass of the vehicle, damping of all the tires and all this, and stiffness of all this, all were considered both due to gravity and due to moving mass. So this is the equation, vehicle model. You see these centrifugal forces, differential equations. I am telling you these are the specifications. Mass of truck, how much? 2612 kg. Example, pitching moment. These are all standard chart what we got for each vehicles. You can change it also for the present day vehicles. And these are the static wheel loads, and we got the frequencies. 1.52 hertz, 2.14, like that. 6 frequency, whichever is the least is called fundamental frequency. First axle, second axle, third axle, total weight were considered. And here, the bridge model, what is considered is also very important. It is modeled using a conventional FEM, finite element method, and the equations of motion for the bridge can be expressed in the following equations, which you can go through. Vehicle bridge model interactions, vehicles were developed, and bridge parameters, what? ASTO bridge, slab type, PSC girder bridge, all this 6 meter, 8 meter, 10 meter spans, first bending moment, second bending, bending modes, second bending modes, that is in hertz, what are the frequencies, all these were analyzed for type 2, type 3, and type 4, pre-stressed concrete girder type and slab type bridges. And all the inputs and outputs as per this, first mode of the bridge is very dominant. To reduce the bridge dynamic response, we have to use what is known as tuned Morse damper. Already it has to be tuned to the particular frequency, that is called TMD. That also has to be adopted. It will be positioned at the center of the bridge, TMDs. These are all they are doing already in Japan and in China. Tuned Morse dampers even we are using here also. Basically it's a SDOF system. It adds to a modes of vibration. You have the mass, spring, damping, modal mass. Okay, I am showing you the sketch, and we have developed the equations and magnitude of displacements versus frequency, time history analysis using the software. This causes a very strong dynamic interactions you are getting in TMD. And what is your target mode? We can check it. Is it okay or not? What frequencies I am getting? All these optimum tuning conditions were used in the TMD. And also, a lot of proposed tuning conditions are already available, standard one, using Hartog's tuning conditions, and it has to be tuned as per this mass ratio, TMD frequency, damping values, all that. Hence, we get critical damping position was as per Zoy is one of the good contributor, and the equation was used from that research paper, and our analysis were matched with that, keeping the mass ratio as constant. Different parameters, mass, stiffness, and damping, all were calculated. With increase in TMD mass ratio, what happens? Decrease in optimum frequency, increase in TMD inertia force. These are the two conclusions. And the mass ratio, how much? Very small, 0.01 to 0.04 is generally recommended. 1% is selected in this study, usually very small. It is 0.1 to 0.4, 0.01 also. In practice, there is limit to the mass, which can be added due to space and static stress limitations are there in practice. See here, these are the tuned mass dampers modeling as per what we used to study in MTech or BTech, your structural dynamics. Differential equations were considered, and time, the increasing force between bridge and the tuned mass dampers. These equations were developed. Final equations of motions of the bridge, which is a diagonal, and also mass matrix is diagonal. Second one is C matrix, that is called damping matrix. Third one is stiffness matrix. Whole thing is equal to different forces acting on it. So what happened, the results were what we got is different axial positions. What is the deflection at midspan for the first axial position when the span is 6 meters? With the TMD, without TMD, time history analysis were considered. Similarly for different spans, 6 meter, 8 meter, 10 meter, 16.76, standard one, 24.38, 30.48, and all the results if you combine without TMD, with TMD, what is the deflection in mm? Acceleration is how much? Without TMD, without tuned mass damper, and with tuned mass, different span lengths. These are the observations. Therefore, finally, I wanted to conclude is performance of TMD may be influenced by dynamic characteristics. When the natural frequency of the vehicle matches that of the bridge behaves like a vibration absorber. Bridge will become vibration absorber. As you have seen in TMD, first mode is generally reduced and higher modes remain unchanged. First mode will be the largest contribution to the all these responses, and mainly we should take care for the first mode itself. These are only some of the important observations, conclusions. What he is telling, the TMD for reducing the force distribution is more effective than the case with only two trucks moving side by side. Okay, some of the control strategies, we got the conclusions. So now the question is based on so much of work, how do you say you are correct or not? We should go for publications, and it should be a good publication. If not, it won't be okay. So I went and presented at IIT Kharagpur in 2002 itself. All were international conferences at IIT Kharagpur. IIT Kharagpur. Then free vibration slant Skew bridges, some of the things from Bangalore University conferences. Then I went to Coimbatore. Then it was agreed in IIT Kharagpur. 3-4 papers all in IIT conferences. Then I went abroad. And it was a world conference on earthquake engineering. I went and presented at Vancouver, Canada. It's a world earthquake conference, 13th world conference on response of slanted bridges. I went and presented. I got some ideas. Then it was presented in BITS Pilani. Then it was also in all of the international conferences, even in Kuwait. Then it was all mainly from Kuwait and from world conferences. Then I presented in person in San Francisco, that the topic was on this vibration control under dynamic loading. All were presented, published in the journals and conferences in world over. Therefore, we got the confidence that this is a topic to be considered. Still, it is to be improved. Therefore, active structural vibration, you see number 18. This abstract was submitted on the 9th Canadian Conference, Ottawa, Canada. All were published. So, therefore, finally, this give us the confidence to move further. Those who want to do further work, they can please go through these papers and please improve this over any other skew changes, model studies, and you can change the spans. This is the idea. And now I wanted to thank you for hearing all my this one. Thank you for giving me the opportunity. Now over to the audience. Thank you, sir.
Uh, Thank you, sir. So now I request any of the participants, if you have any queries or any discussion on the topic, what the sir has covered in the presentation, uh, they can talk to the resource person.
Now to transfer. Okay. Okay, sir. Any doubts
Okay.
or?
I think right now this at this junction there are no any queries.
They
So
can mail
yeah,
me. Mail
yes,
me.
yes, yes, yes. I will put your contact in the chat box
Yeah.
so that they can contact you directly.
Okay.
Thank you very much, sir, for enlightening us regarding the how the bridges has to be considered for the dynamic effect, because all the moving vehicles will have an impact on the pavement or the decking system. So obviously, while designing any bridge, so the dynamic effect on the bridge has to be considered again in particularly when the bridges are aligned with some skew angles. So definitely there will be a additional uh, the stresses are going to be developed, and that has to be analyzed, and then only the bridge can be a stable and can serve for its intended life. So in this regard, you had highlighted the analysis of a skew bridge. So on behalf of the KLS Institute of Technology and ISTE and AICTE, I would like to thank you for your sharing your knowledge to the audience. Thank you, sir.
Thank you. Thank you. Bye.
Thank you, sir.